I'm pleased to be here today, and I really want to thank Emrys for organizing this whole series of lectures. When he asked me to talk last semester, I said, well, what do you want me to talk about? And he said, well, hopefully we'll have a new administration, and maybe alternative energy will be more important next year. And I'm pleased to say that his predictions were correct, and I'm glad to be here. So anyway, I'll be talking today, and my title's a little misleading. I'm going to be going in this direction: policy, technology, and then science. Energy, how we use it, how we get it, who uses it, and where we get it, impacts almost every major global issue today. And these issues are only going to become more and more serious as the reserves that we have decrease and as the demand for energy increases. I want to take a look at some of these issues: where we get it, how we get it, who uses it, and how we use it. Basically, our energy problem is a fossil fuel problem. If you take a look at the energy use in the United States, you'll see that by far we get most of our energy from petroleum. Here in 2004, that accounted for about 40%. Closely behind that, at a close second and third, are coal and natural gas at about 20% each. And then nuclear and renewables, both hydro and non-hydro renewables, account for less than 20% of our total energy use. The reason that this is a fossil fuel problem is that most of these are finite resources. In fact, all of these fossil fuels are finite resources. There are limited reserves, and there will be an increasing demand. The second problem is that this distribution of reserves is not uniform, and it can lead to a great many social and political issues. And furthermore, there is pollution associated with the combustion of these fossil fuels. Let's just take a look at the limited reserves. Back in the 50s, Hubbard developed this peak oil production curve. So here he was in 1950. He took a look at the proven reserves in the 50s and then made some assumptions about what would happen. And back in the 50s, he basically said, we are going to be close to out of oil in 2200. Now, since his first curve, which is essentially a bell-shaped curve, there have been a lot more sophisticated models, but most of them don't tell a different picture. Most of them show us at peak oil here at about 2010. There are a few outliers suggesting that will last a little bit longer, but I think the problem is pretty clear. Oil is not an infinite resource. There's some talk about replacing our dependency on oil to natural gas, but this doesn't change the situation much. Here are natural gas reserves, most of them in the Middle East, second in Eurasia, Africa, Asia, North America, Central and South America, and Europe. And there have been some studies, and although they're not precise, but if we were to replace the use of oil with natural gas, the reserves of natural gas would be about 50 years. So this is not an option for replacing our dependency on oil. When we look at coal reserves, the situation is a little bit brighter, but there are issues involved. If we use coal at the rate that we use it now, here's what we find is we have about 234 years of reserve. Russia has about 508, China has about 48, India 200, Australia 200, and then the rest of the coal is produced here, and I don't have the data for how long those reserves are. But the picture's clear. There are issues. Now, let's take a look at who's using the energy now. If we take a look at a picture of the world from outer space, and basically this reflects energy use. All this is primarily the use of electricity and lights that are on. What we see is there is a concentration of energy use here, especially in the eastern part of the United States, here in Western Europe, and here in Japan. Now, if we compare that energy usage to basically where the population of the world is, we see quite a different picture. If we take a look at population density and compare that to, basically, this is an energy density map. This is a population density map. High population density here in India, high population in China, high population in Europe. These two maps don't overlap. And our problem with limited fossil fuel reserves are only going to get worse when the economies of these nations continue to increase. They start using energy at the rate that these energy hogs do. We're going to have a real problem. This problem is highlighted in this graph, and this shows the world market energy consumption from 2005 to 2030. Now, the good news is that the developed nations, mostly here we have European nations, the US, North America, their use is going to be constant. There's very little increase in their use of fossil fuels. But these developing nations, most of Asia, South America, and Africa, and remember, the high population densities in parts of Asia, here's what we're seeing, is the increase in the energy usage is primarily due to economic growth in those regions. And while economic growth is good, it is going to put some strain on our world. Contributing to that strain is also where this oil is distributed. It's not surprising to anyone in this room that the largest oil reserves are right here. And I wouldn't be a bit surprised that if you moved all the weapons of mass destruction away, you'd find those oil reserves, right? So, in any event, here we are, 6 to 12 years of oil reserves. If we go to coal, the situation is a little bit different. North America, Russia, India, and China have the largest coal reserves. But as I mentioned previously, that's only going to delay the problem. So it's not going to be a few decades, it might be a few centuries. And I think all of us have some concern about what increased use of coal would mean. So the point that I'm trying to make with showing these graphs is that the distribution of this oil and coal and natural gas and the distribution of where the reserves are and where it is used leads to a lot of political and social tension. And it's not only political tension from country to country, but also within countries. And I've just picked a handful of pictures from the media to demonstrate that. This is Nigeria. And basically, there are vast oil reserves in the Niger Delta. Oil companies come in, and a few people really benefit from that, while the majority of the population lives in places like this. We all know in the U.S. how we're affected by the oil issue. This shows last summer, or maybe last year when actually it's probably last year when the prices rose to close to $5 a gallon in some areas of the country. Aside from that, there are also issues with protests. I think this is from the U.S. This is in the North Sea where there are protests about offshore drilling. And this is in Venezuela, and this had to do with a protest associated with the change in the management of the state-operated oil company. So, what are we going to do about it? Well, before I go to what are we going to do about it, look at another issue, and that is the pollution associated with fossil fuel. So if we look at combustion of fossil fuels, here's what we see. You burn fossil fuel, you get carbon dioxide, you get water, in theory, and in practice you get a whole bunch of other species. These, as well as carbon dioxide, are greenhouse gases. Now, the good news is that there are things that we can do with these. And as you can see from these projections, here's the projections for sulfur dioxide, the projections for nitrogen oxides, and the projections for mercury. Those are projected to decrease, and that's primarily due to the technology that we can develop to capture those. The problem is with CO2, and it's an unavoidable problem. Now, while there are some ideas about how to sequester CO2, it's a gigantic problem. And you can see the same group that made these predictions for the next 20 years made this projection for carbon dioxide over the next 20 years. So how do we solve this problem? Well, there's really going to have to be a three-pronged approach, and that is changing human behavior, having government policies that promote the use of non-fossil fuels or renewable fuels, and then also the development of technology, both evolutionary and revolutionary. In the remainder of my talk, I'd like to take a look briefly at these two and then focus a little bit more on the technology and the things that we're doing at Alfred University. This is human behavior. Okay, it's not. It's a graph. So in any event, what I'm showing here is a graph of the electricity use per capita and the Human Development Index. Now, here's what's interesting about this. When you're not using very much electricity and you start to use it, there's a rapid increase in the development index of these countries. But you get up to a certain point and there's a plateau. So here's North America out here. Here's Canada, here's the US, here are other developed nations. The point is, the more you use is not going to change the quality of our life that much. And so there are all sorts of things that we can do to not use as much energy and still maintain the quality of life. I know from a personal standpoint, my mother would be appalled if she knew how many lights that I left on in a given day. The way that I use energy today and the way my family used energy when I was a child are just unbelievably different. This is another graph which shows the gross domestic product versus energy efficiency. Again, here are the developed nations, here are developing countries. And so I think as a people, what we need to be thinking about is how do we move people up into this area, highly productive, where presumably there's a high human development index and highly energy efficient. Let's take a look at what government policies do and can do. In the United States, there are a handful of agencies that deal with energy, the most notable being the U.S. Department of Energy. Right now, they spend about $3.6 billion, or I should say they're allocated about $3.6 billion for basic research. They also host a number of other programs that are really set towards getting industry, academia, and other government agencies involved. One is the Solid State Energy Conversion Alliance, which was started in 1999 to try to develop solid oxide fuel cells and to make them commercially viable. They also are the host of the Clean Coal Initiative and more recently the Solar Energy Technology Program, Solar America, which goal is to get cost-effective or cost-competitive photovoltaics by 2015. Other agencies which get involved in the mix are the Environmental Protection Agency. Of course, they regulate the emissions, and they're primarily associated with the emissions of energy and industrial production. National Science Foundation funds basic research, some of it related to energy. Perhaps surprisingly, the Department of Defense and NASA also support alternative energy research, and primarily for logistics and for making portable energy for both defense and space missions. And then on a more local level, we have agencies like NYSERDA, the New York State Energy Research and Development Authority, which takes a little bit of your electric bill and puts it into a pot that gets used for research as well as programs that teach people how to install photovoltaics, for example. Now, one of the things, though, is to get an increase in these renewables, I think we're going to have to see additional government policies, incentives. We have things like tax breaks for putting in solar panels into your house, but a lot more is going to be needed because ultimately the consumer relies on what's the price. What I want to do now is move a little bit from our discussion of government policy towards technology. And I want to talk about federal funding for energy research. With the new administration, there has been a barrage of reports talking about how do we move the energy agenda forward. This one is a series of facts I got from the Council of Energy and Education Leaders, and some of these facts are pretty sobering. Take a look at this. Less than 2% of federal R&D funding is devoted to energy compared to 10% in 1980. That's about 2% of the total price of the Apollo mission. And I'm sure I'm not the first to say it. I'm sure there have been several politicians before me saying that. But imagine if we could take sort of the national interest in the space mission back in the 60s and put it towards getting a good, solid, renewable energy portfolio. I'd also like to make comparisons here between the energy sector and health. If you look at the total revenue of the energy sector, it's about $1.9 trillion compared to health, which is about $1.7 trillion. So in terms of an economy and revenue, they're similar. DOE Energy and Science, its allocation for energy research, or its allocation period, was $6 billion. Only 3.6 went to basic research, and not all of that research was towards energy. Compare that to the National Institute of Health, which has $29 billion in funding. Also take a look at what the corporate sector is doing. Here we have $1.2 billion, and while, you know, in my world, billion sounds like a lot, but compared to this $1.9 trillion, that's less than 0.25%, a quarter of a percent of the revenue. Compare that to corporate research in the health sector, particularly in the pharmaceutical companies, where the amount of money spent on research approaches 20% of its revenue. The news isn't all bad. With the new administration, there has been a lot more talk about alternative energy. This is a handout prepared by the Department of Energy. It was a report to the Basic Energy Science Advisory Committee, and it talked about getting energy for a secure and sustainable future. Here are some of the things that they noted. A need for materials with unprecedented performance, catalysts, sequestering carbon, nuclear power, solid-state lighting, solar economy for buildings, a hybrid electrical grid, advanced transport, that means making things that use what hydrocarbons we have more efficient, and then finally solar fuels. One of the things as a material scientist that I was incredibly pleased with is throughout this report there was an overwhelming emphasis on new materials. Also in reading this brochure I noticed something, and if any of you are involved in materials, you know that the word nanoscience and nanotechnology was thrown around a lot in the past decade. Notice if you start to see this term, control science, more and more. So control science, in particular in this report, basically was saying the ability to manipulate matter to do what you want it to do, which is the same thing that we said about nanoscience, but it's just interesting. Let me know if you see that more and more. So the thing I want to point out is the time to act for these new energy technologies is now. If you go to any tech transfer presentation, you're going to see this S-curve. And what it talks about is the time and effort involved in developing some technology versus its performance. It breaks it down into basic research. At some point, this basic research, somebody decides they can make money on it, and it's a new invention. And then there's this period of technology development that's very steep, where performance increases, 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 and then levels off. Now, the length of this time from here to here, does anyone want to guess what's an average length of that time? Well, I think it depends. I mean, it ranges incredibly. Some people show 2-year time spans for little inventions. Some people show decades worth of a time span. Let me show you one related to energy. Here's the example for the solid oxide fuel cell. Now, this is a device, it's an electrochemical device that consumes fuel much more efficiently and produces energy much more efficiently than, say, the combustion engine. I'll show you some data on this later. But let's take a look at the time frame. Here, back in the 1800s, we saw much of the fundamentals of electrochemistry being discovered. In 1900, we start to see the use of the term solid electrolyte, which is a material that's critical to the operation of this device. Another 50 years, we start to see actual cells, actual devices start to be tested in academic laboratories. Then somewhere here in the 60s, somebody decides that, hey, maybe this is a good thing, maybe we can make some money on it. I will put in for a patent on it. And then in the 70s, so 10 years later, we start to see the first generation of material sets that are going to make this a reality. And then finally in 1986, so look at here, from 60 to 86, we finally see the first generator piloted. Solid oxide fuel cells are still not considered to be, are not in widespread commercial use today. That's why in 1999, the Department of Energy started SECA in order to try to commercialize these. So this thing that has an efficiency that's probably double that of the combustion engine, from 60 to 86, we just got to see some that were in use. They're still not ready for use in cars. And now we're talking about new S-curves with new materials development, trying to get them to operate at lower temperatures so that they can actually work in a variety of different applications and have a reasonable lifespan. So, in the remainder of this talk, what I want to do is I want to talk about what we're doing at Alfred University related to alternative energy and energy-efficient products. Whenever I give a talk about the research in our School of Engineering, this is a slide I show. And the point that I want to make out is I think we have something like 24 faculty members, and this is the number of faculty members working on technologies related to alternative energy or energy efficiency. So it is a very, very large part of our research portfolio. Many of us are working on solid oxide fuel cells. Some of us are looking at how you can generate hydrogen from cleaner sources. Some of us are looking at wind power, biomass gasification, solar power. This is concentrated solar power, photovoltaics, and also hydrogen storage. What I'll do in the remainder is just take a brief look at some of these projects and just show you some of the issues that are involved. For the scientists in the audience, I apologize because I'm not going to go into much detail. And if science is not your thing, but I doubt if it wasn't your thing, you probably wouldn't have shown up for this lecture. I apologize if I go too far in the other direction. So anyway, let's talk a little bit about solid oxide fuel cells. So a solid oxide fuel cell is an electrochemical device. How it differs from combustion engines is that it basically moves oxygen through a membrane and makes it interact with a fuel in a very controlled manner and in a manner that generates electrons, and then those electrons are converted, or they are basically electricity that can power some sort of load. The difference between it and a combustion engine is when you burn fuels in a combustion engine, you generate a lot of heat, and that heat is basically disorganized energy and it can't be used for work. So if you take a look at electrical efficiency versus power, here you see combustion engines, diesel engines, gas turbines, and up here, and these are at about like 10 to 30% efficiency, and you take a look at something like a fuel cell, and now you're starting to talk from 40 to 80% efficiency depending on its size. The solid oxide fuel cell can burn many different types of fuels. It can burn hydrocarbons. This doesn't do anything for the CO2 problem we talked about, but it also can burn hydrogen, and in fact that makes a nice cycle, hydrogen plus oxygen, and you get water. The real key here is where is that hydrogen coming from, and I'll talk about that later. The solid oxide fuel cell is comprised of a stack of different materials. Here's this electrolyte, an anode, a cathode, and interconnects. So they're basically this three-layer device. Two interconnects are stacked on either side, and then there's another fuel cell, interconnect, fuel cell, interconnect, fuel cell. This is a materials nightmare. You have all these different materials that need to perform certain functions. They have to do it at 1,000 centigrade, and this just presents a lot of problems. So when I showed you that S-curve that took 25 years to get to a device that worked, a lot of that was related to how all of these materials behaved with one another. There's several of us working on this. The material in the center that I talked about was this electrolyte, and what it does is it moves oxygen through something called a vacancy. So here's a crystal structure. If you put a dopant into it, you create what are called vacancies, and basically that allows this oxygen atom a place to go. And so that oxygen ion moves by going into that vacancy. It leaves a vacancy behind it, and it transports through this membrane. One of my colleagues, Dr. Cormack, who's in the back, is studying the formation of these vacancies and how they sit in these crystals using computer modeling. One of the problems is that not all the vacancies that are there actually contribute to the conduction process, and he's trying to figure out why. So basically he puts ions in a box and he sees where they want to sit, and he looks at the energy and tries to determine why they aren't moving. Okay, so that's one of the things that we're doing. Moving to another area that we're working in, and we're also looking at the cathode. This cathode is one of those layers that sits on the opposite, or on one of the sides of the electrolyte, and it provides electrical contact to the cell. It also serves an important function in that it disassociates oxygen from the atmosphere so that it can get into that electrolyte. So basically, here's the cathode, oxygen is here, it's at this surface that this process occurs. We take oxygen from the atmosphere and we actually get it to go into this membrane. The cathodes that are out there are a type of material called a perovskite, and there's a great deal of work going on trying to develop better ones by changing the different elements within that perovskite structure. For example, this is something that Scott Mister's group and my group is working on, and I'm showing some of the work of one of my grad students, Jae-Il Jung, and Scott's previous postdoc, James Evanstone. So basically, we're looking at things like, if you change this composition, how does the electrical conductivity change? So here we show, if we put more cobalt in, we see an increase in conductivity, and that influences how these things work. We also look at their thermal expansion. If we change the atoms that go in there, how do they expand? And that's really important for stacking these things together and not having it break apart if it's heated to a high temperature. And then also we look at how it reacts, and this is work in Scott's group, how it reacts with other gaseous species. So you don't want something in this fuel cell, you take it to a high temperature and all of a sudden it reacts with the atmosphere and breaks apart. So these are all issues to deal with performance and reliability of this energy efficient device. I'm going to, in the sake of time, I'm going to skip that slide, move on to hydrogen generation. The great thing about hydrogen is no carbon dioxide. But as I mentioned earlier, what's the source of the hydrogen? A lot of the immediate use of hydrogen really involves extracting it from fossil fuels. And I quite frankly don't see the benefit of that. To really break that cycle of CO2, we are going to have to get that hydrogen from a clean source. And that clean source is water. Now, this is a possibility. Using sunlight to power an electrolysis reaction that allows you to get hydrogen and oxygen. However, this is a very energy-intensive process and it's not very efficient. So I think there's been work on it for several decades and you will still continue to see work on this. Let me just show you one piece. Recently, we looked at a bunch of different crystal structures, and basically these had never been looked at before as a possible catalyst for hydrogen generation. All of these structures have tunnel features, and we did this because some of the previous work in the literature showed that materials with these tunnels did catalyze the reaction, and there's some thoughts about why maybe these tunnels served as nests for other particles that would promote this reaction. And so this just shows an example of some of the stuff we did. This is very beaker-oriented research. We basically put our materials in water, shined a light on it, took a look at the hydrogen that was produced, and then looked at it over time. Well, the one thing is we learned a lot. We learned that there were differences in these materials. The sad part is we haven't done anything better than was already out there. In fact, the best performer was the one that was shown to work 30 years ago. So anyway, this is a continuing effort on our part. How are we going to store it? Not like this. This shows a concept that Jim Shelby and Matt Hall looked at, and that was storing hydrogen under pressure under these little spheres. So if one of these little spheres breaks, you don't get this, right? And in fact, the chance of these little spheres breaking was quite low. So that was one set of research. And that's all I'm going to say about that in keeping my time in mind. Here's a story that I think is quite interesting, and I'd like to spend a little bit more time about this. Before I go into there, here's the compelling case for solar. Here's our global consumption of energy. That's how much solar energy hits the Earth. So if we could just harness, a small fraction of that, we would be meeting our needs. We have been trying to do it as a society. One way is concentrated solar power, and this shows some of the different concepts for concentrated solar power. And all of these are operating, and they are real, and they are operating on a small scale. If you can think of this as a small scale, each of these is probably 12 feet long, and there are acres and acres of these. This is called a trough collector. This shows this trough collection system. There are about 9 of these plants in the southern United States. One is the Harper Lake facility. Here's the problem. Currently, 12 cents per kilowatt hour to generate this. And in order for it to be cost competitive, it needs to get down with the alternative methods of generating electricity, hydro or burning coal. Here's how this thing works. Here's a mirror, so concentrating mirror. Sun comes in, hits this mirror, and it's directed towards this tube. In the center of this tube is a fluid. That fluid heats up. That fluid gets pumped to a generator. It causes a turbine to move. It generates electricity. That's the basic design. These mirrors actually move to track with the sun. But it turns out that it's this tube here is one of the problems. It represents 20% of the construction costs. Each of these tubes costs about $1,000. And the failure of these tubes represents about 2 or 4 cents per kilowatt hour for the price of solar generated by this technology. We got involved in this, and by we I mean Dr. Carty and I got involved in this because a company came to us and said, we're having problems. This is what some of our tubes look like. This is not a fluorescent light tube. This is a solar energy receiver. What happens is there's a coating in this receiver. These tubes are inside a glass cavity, and to prevent convection loss, they're evacuated. What happens is these things are out in the desert. They're seeing temperature variance from 110 degrees at daytime, probably close to freezing at night sometimes, 70-mile-an-hour winds. And the fact is there are problems here. Leaks occur, air gets in, it degrades this coating because this coating is at 400 or 500 degrees Celsius. It degrades the coating comes off, coats the inside of the glass, and basically makes this tube ineffective. So we had some ideas about how we could change this. What the company was doing is they were taking these spent tubes and they were basically scratching the coating off and putting them back into place. Now the problem with that is it wasn't efficient. To have an efficient coating, you want one that absorbs sunlight, but then one that doesn't emit black body radiation at the temperature at which they're operated. So that's a way to lose heat. So what we want to develop is something called a solar selective coating, and the original ones were selective. Here they're absorbing a lot. They go from the visible to the IR, and their absorptivity decreases, and that's what we want. However, when they were taking these selective coatings and putting, and my pen has run out, and replacing them with stainless steel, this is the behavior they're getting, and so the efficiency is going to go down. They tried some alternatives. They tried painting them black, and this is the behavior of that black paint, which is also not very good because that black paint is not selective. So we had an idea, and our idea involved embedding absorbing particles in a glass matrix using an enameling process. This is the same process that's used to put coatings on your washing machine and your hot water heater. And tailoring the composition to get that solar selectivity. And so we developed a number of coatings, and we see some benefit. Here we see some selectivity, high absorption in the visible, and then it starts to decrease in the IR, and that's a great thing. If we manipulate temperature, or if we manipulate how much of these particles we put in, we can change the properties of it. And so in that respect, it was successful. One of the things that we didn't count on is that there's an absorption band associated with glass that really limited the effectiveness of this out in the IR region. But in any event, these were tested in the Harper Lake facility, and the company we worked for, I believe, changed hands, and so we never really found out how they performed in the field. So anyway, we didn't stop there. We're now working with another company, and in fact, Aladdin Galil, who's in the audience today, is working on one of these technologies. So, and looking at a different way to make these. I'm looking at the time, and I'm supposed to wrap up at 1 o'clock. I had a few more stories of different technologies for you, but I'm going to skip over those. If you have any interest, I would be glad to share them with you. But basically, let me go to my conclusion slide and wrap up with what I tried to convey today. So basically, what I started off with is something that you all know. Energy impacts most of today's global, important global issues. Getting out of this cycle will take a three-pronged solution, especially for the fossil fuel program. Our consumer, our human behavior, how governments regulate and incentivize development of new technology, and the technology itself. And then what I wanted you to walk away with is the notion that we are doing a lot of research directed towards energy here at Alfred University. And if you were to stop me or any of my colleagues and want to ask them about what they're doing, I would imagine they would be more than willing to talk your ear off about it. So, in any event, thank you for your attention.